Hello, welcome to my talk at MFCS 2020. My name is Mateus de Oliveira, and I'm a researcher at the University of Bergen in Norway. This is joint work with Lars Jafke, also from the University of Bergen, and Hans Raj Tiwari from Charles University. We are knowledge support from the Trond Mohn Foundation, from the Research Council of Norway, and from the Czech Science Foundation. The title of our work is Compressing Permutation Groups into Grammars and Polytopes, a Graph Embedding Approach. Usually, when dealing with groups from a computational point of view, two representations come to mind. The explicit representation by the multiplication table of the group, or a more compact representation by a set of generators. In this work, we will explore three alternative approaches for representing groups in a compact way. First, by embedding groups in connected graphs parameterized by tree width and maximum degree. Second, by using context-free grammars. And third, by representing groups as polytopes. The nice thing about these three representations is that they are all interconnected. More precisely, efficient representations using graphs of small tree width and maximum degree imply efficient representations using grammars, which in its turn imply efficient representations using polytopes. In the opposite direction, lower bounds on the sides of representations by polytopes imply lower bounds on the sides of representations by grammars, which in its turn implied lower bounds on the size of representations by graphs of small tree width and maximum degree. I will start by describing how to embed a permutation group into a graph. We will be representing a permutation of the set 1 to n as a string over the alphabet 1 to n, where each symbol occurs exactly one time. For instance, the string 2, 1, 4, 3 represents the permutation of the set 1 to 4 that sends 1 to 2, 2 to 1, 4 to 3, and 3 to 4. The symmetric group Sn is the set of all permutations of the set 1 to n. For us, when talking about a permutation group, we will always mean a subgroup of Sn for some natural number n. The composition of a permutation beta with a permutation gamma is the permutation obtained by first applying gamma and then beta. More generally, if beta is a permutation and S is a set of permutations, then the composition of beta with S is a set obtained by composing beta with each permutation in S. Now, let's talk about the relationship between permutations and graphs. When speaking about a graph with m vertices, we will always assume that the vertex set of the graph is the set of numbers between 1 and m. Let G be a graph with m vertices. An automorphism of G is a permutation of the set 1 to m that preserves the edge relation of the graph. In other words, edges are sent to edges and non-edges are sent to non-edges. Intuitively, an automorphism is a map that preserves the shape of the graph. Consider, for instance, the complete binary tree with 4 leaves. The permutation that swaps each leaf with its sibling is an automorphism. The automorphism group of a graph X is a set of all automorphisms of X. We say that the automorphism group of X stabilizes a subset U of vertices if each automorphism of X sends elements in U to elements in U. For instance, the automorphism group of a tree stabilizes the set of leaves of the tree, because leaves can only be mapped to leaves by an automorphism. It can be shown that the set of bijections from U to U obtained by restricting each automorphism of X to U is also a group. For instance, in our example, the group obtained by restricting the automorphism group of the complete binary tree to its leaves is a group of permutations of the set 1 to 4. Now, we are in a position to state the main definition of this work, which is the notion of graph embeddability of a group. We say that a subgroup G of Sn can be embedded in a connected graph X if G is equal to the group obtained by restricting the automorphism group of X to its first n vertices. In 1969, Babai and Bauer showed independently that any subgroup of Sn can be embedded in a graph of size at most n plus the number of elements in the group. Note that this upper bound can be as large as n plus n factorial. Therefore, given a group G, it is an interesting question to determine what is the smallest number of vertices in a connected graph embedding G. We call this number the graph embedding complexity of G. Note that the graph embedding complexity of a subgroup of Sn can be as small as n. For instance, Sn itself can be embedded in the complete graph with n vertices. On the other hand, it is still an open problem whether the alternating group An can be embedded in a graph of size polynomial in n. We note that the graph embedding complexity of a group can also be defined with respect to a more restricted class of connected graphs. In this work, we studied the graph embedding complexity of groups in classes of graphs parameterized by tree width and maximum degree. We will also establish connections between graph embedding complexity, formal language theory, and linear programming theory. Next, we will show how to represent finite permutation groups using context-free grammars. Context-free grammars are a formalism for the representation of possibly infinite sets of strings. This formalism is very well studied in formal language theory and has numerous applications to compiler theory and programming language theory. In general, they have the same expressive power as push-down automata. In the context of this work, we will only be considering grammars that generate finite sets of strings, all of which have the same size. Given a set L of strings of length n, a relevant complexity measure is the minimum size of a grammar generating all and only those strings in L. This measure is called the grammar complexity of L. Intuitively, the grammar complexity of a set of strings is a measure of how much this set can be compressed using grammars. In this work, we will be interested in a more robust notion of grammar complexity of a set of strings, which allows one to first permute the coordinates of strings in the set according to some permutation alpha. More precisely, let W be a string of length n, and alpha be a permutation of the set 1 to n. We let perm of W alpha be the string obtained by permuting the coordinates of W according to alpha. Now, let L be a set of strings of length n. Then perm of L alpha is the set of strings obtained by permuting the coordinates of each string in L according to alpha. The symmetric grammar complexity of a set of strings L is the minimum size of a grammar generating some permuted version of L. Our main result establishes an upper bound on the symmetric grammar complexity of a group G in terms of structural parameters of connected graphs embedding G. Additionally, this upper bound works even with respect to cosets of G. The first parameter we consider is the maximum degree of a graph. The second parameter is the tree width of a graph. Intuitively, this parameter provides a measure of how much a graph looks like a tree. Although we will not formally define the notion of tree-width in this talk, it is worth noting that several interesting classes of graphs have constant tree-width. For instance, trees have tree-width at most 1. Series parallel graphs have tree-width at most 2. Alterplanar graphs have tree-width at most 2. K-alterplanar graphs have tree-width O of k, and so on. Now that we have introduced our parameters, we can formally state our main result. Let G be a subgroup of Sn and beta be a permutation in G. Suppose that G can be embedded in a connected graph X with m vertices, tree-width k, and maximum degree delta. Then, the symmetric grammar complexity of the coset beta times G is upper bounded by 2 to the O of k delta log delta times m to the O of k. In particular, subgroups of Sn that can be embedded in graphs of bounded tree-width, bounded degree, and size polynomial in n have symmetric grammar complexity polynomial in n. Next, I will show how the results described so far can be used to establish a connection between group theory and linear programming theory. Recall that a polytope in Rn is the convex hull of a finite set W of vectors in Rn. Alternatively, such a polytope may be represented as the set of solutions of a finite set of inequalities on n variables. An extended formulation for a polytope P is a polytope Q in a higher dimensional space, which can be mapped to P by a linear projection. Extended formulations are widely used in linear programming theory for two reasons. First, linear optimization problems, whose set of feasible solutions can be described as a polytope in Rn, can be recast as linear optimization problems using extended formulations of this polytope. Second, many important polytopes used in combinatorial optimization theory require a superpolynomial number of inequalities to be defined in Rn. Nevertheless, some of these polytopes admit extended formulations of polynomial size. Obtaining polynomial size extended formulations for polytopes used in combinatorial optimization theory is often a very non-trivial task, and in many cases, provably impossible. Therefore, the development of general techniques for the construction of small extended formulations for interesting polytopes is a fundamental quest in linear programming theory. Our main result, relating the symmetric grammar complexity of a permutation group with its graph embedding complexity, allows us to contribute to this quest when it comes to the extension complexity of polytopes representing groups. Before showing you how, let me observe that polytopes can be used to represent sets of strings in the following way. First, we assume that the alphabet over which the strings are defined is numeric, say, the set of numbers between 1 and n. Then, given a string W over this alphabet, we let hat W be the vector in Rn where each coordinate is equal to the corresponding coordinate in the string W. In particular, permutations can also be represented in this way. Now, let L be a set of strings, all of which have the same size. Then, the polytope associated with L is the convex hull of the vectors corresponding to strings in L. A result from Pessin, Campet, Rousseau, and Selman states that for each context-free grammar and each n, the polytope corresponding to the set of strings of size n generated by the grammar has extension complexity polynomial in the size of the grammar and in n. Additionally, a corresponding system of inequalities of size polynomial in n and in the size of the grammar can be constructed in polynomial time. Intuitively, this system of inequalities simulates the behavior of the CYK parser for the grammar in question on a string of size n. This implies that the extension complexity of a set of strings of length n is upper bounded by a polynomial in its symmetric grammar complexity. And where is the connection with group theory? Well, if G is a subgroup of Sn, encoded as a set of strings over the alphabet 1 to n, then the polytope associated with G is the convex hull of permutations in G. In particular, the polytope associated with the symmetric group Sn is the convex hull of all strings representing permutations in Sn. This polytope is well known in linear programming theory as the n-permutahedron. It can be shown that to define the n-permutahedron in Rn, one needs 2 to the omega n linear inequalities. On the other hand, a result from Goemans states that the n-permutahedron has extended formulations with O of n log n variables and constraints. The technique used by Goemans to upper bound the extension complexity of the n-permutahedron has been generalized and used to show that polytopes corresponding to other important classes of groups also have small extension complexity, including the polytopes corresponding to the alternating group on n elements and polytopes corresponding to finite reflection groups. Nevertheless, techniques to prove non-trivial upper bounds on the extension complexity of polytopes associated with general permutation groups, based on structural properties of these groups, are still lacking. Our next result is a contribution in this direction. More precisely, by combining our main result with the upper bound on the extension complexity of a set of strings representable by a context-free grammar, established by Pesan, Quimper, Rousseau, and Selman, we obtain an upper bound on the extension complexity of a permutation group G in terms of structural parameters of connected graphs embedding G. Additionally, this upper bound works even with respect to cosets of G. The formal statement of our theorem is the following. Let G be a subgroup of Sn and beta be a permutation in G. Suppose that G can be embedded in a connected graph X with m vertices, tree width k, and maximum degree delta. Then, the extension complexity of the polytope corresponding to the coset beta times G is upper bounded by 2 to the O of k delta log delta times m to the O of k. Now, let's discuss some trade-offs relating the index of a group and the size, tree width, and maximum degree of graphs embedding that group. I have already mentioned that any subgroup of Sn can be embedded in a graph whose size is roughly the number of elements in the group. The problem is that such a group may have up to n factorial elements. Classifying which groups can or cannot be embedded in connected graphs with much smaller number of vertices is an interesting problem in algebraic graph theory. Indeed, constructing an explicit class of groups with superpolynomial graph embedding complexity is still an open problem. This is still open even for the alternating group An. Recall that if G is a permutation group and H is a subgroup of G, then the index of H in G is defined as the size of G divided by the size of H. By using the fact that context-free languages are closed on a union, and the fact that the symmetric grammar complexity of a subgroup of Sn is equal to the symmetric grammar complexity of any of its cosets in Sn, we can infer that the symmetric grammar complexity of G is at most the index of H in G times the symmetric grammar complexity of H. Now, let's fix G to be the symmetric group Sn. It has been shown by Ellul, Kravets, Shalit, and Wang that the symmetric grammar complexity of Sn is at least 2 to the omega of n. Therefore, by plugging this lower bound in the last inequality, we have that the symmetric grammar complexity of a subgroup H of Sn is at least 2 to the omega n over the index of H in Sn. In other words, this implies that groups of small index have large symmetric grammar complexity. Here, by small, we mean index at most 2 to the Cn for some small enough constant c. By combining the main result of our work with the trade-off we just described, we have the following consequences. First, if a subgroup H of small index in Sn is embeddable in an m-vertex graph with tree width o of n over log n and maximum degree o of n over log n, then m is superpolynomial in N. Second, for classes of graphs of tree width n to the epsilon, for some epsilon is smaller than 1, and maximum degree o of n over log n, we get that the size of graphs embedding groups of small index is actually exponential in n to the 1 minus epsilon. In particular, the graph embedding complexity of subgroups of Sn of small index is lower bounded by 2 to the square root of n on minor closed classes of connected graphs of degree o of n over log n. I will conclude this talk with a summary of our contributions and with some open problems. In this work, we have established new connections between three complexity measures for permutation groups: embedding complexity parameterized by tree width and maximum degree, symmetric grammar complexity, and extension complexity. In particular, we have shown that groups that can be embedded in graphs of small tree width and maximum degree have small symmetric grammar complexity and small extension complexity. Using our main theorem, together with a result of Eloux, Kravets, Shalit, and Wang, established at 2 to the omega n lower bound on the symmetric grammar complexity of Sn, we established a trade-off between the index of a subgroup H of Sn and the number of vertices, tree width, and maximum degree of a graph embedding H. In particular, this trade-off implies that subgroups of Sn of small index cannot be embedded on graphs of small tree width, small maximum degree, and polynomial number of vertices. An interesting open problem is the following. Can one construct an explicit family of groups with superpolynomial graph embedding complexity? It is worth noting that it is still an open problem whether the graph embedding complexity of the alternating group An is superpolynomial. Another interesting open problem is whether one can construct a family of groups whose corresponding polytopes have superpolynomial extension complexity. Interestingly, in this case, it is known that the polytopes associated with the alternating group An have polynomial extension complexity. That's it. I wish you all a nice MFCS, and until next!